Hello everyone, this is for PG Pathsala, paper number 06, Radiation Biophysics, module 14 on computed tomography. I am going to talk about computed tomography today. I am Dr. Ajay Kumar Srivastava from University College of Medical Sciences and GTB Hospital, Delhi. First of all, I give you an introduction about CT. CT image is a display of anatomy of thin slice of body by acquiring and reconstructing the image from multiple X-ray absorption measurement made around the body periphery, and then internal structure of an object can be reconstructed from multiple projections. CT scan takes a large number of data along a thin line of two-dimensional transverse section and reconstruct the structure within that slice. Multiple X-ray projections are formed by scanning a thin slice of the patient body with a narrow X-ray beam rotating around the patient body and then measuring the transmitted radiation with sensitive X-ray detectors. The detectors fully add up the energy of all transmitted X-ray photon. The numeric data from ray sums are computer processed to reconstruct the image. Each pixel of the CT image represent a small volume, as you can see in this here in this figure, voxel, which is the three-dimensional representation of two-dimensional pixel. The average linear attenuation coefficient of each voxel has been derived from computation from series of multiple projections. As you can see here, the CT number is mu pixel minus mu water upon mu water. So in this case, I will tell you about the basic principles of CT image, describe different image reconstruction techniques, and explain about different generations of CT scanners. So by knowing this intensity of transmitted X-ray, intensity of incident X-ray, we can find out the total value of linear attenuation coefficient. If the slice contains 256 slabs of tissue, you can, in this figure you can see 256 slices are there. In that case, the sum of the linear attenuation coefficient values of all these slices is equal to log E n0 upon nx. That means by finding out the intensity of transmitted X-ray and intensity of incident X-ray, we can find out the total linear attenuation coefficient values. And once the linear attenuation coefficient is found out, we can that means the absorption measurement gives me the total linear attenuation coefficient values acquired by the detectors. First of all is the principle of CT computed tomography, which can be explained in 5 steps. The first step is the formation of CT image, is the scanning and data acquisition phase, pre-processing of raw data, image reconstruction, conversion of linear attenuation coefficient into Hounsfield unit, and then display of CT image. Each ray or data point is as in this figure showing here is a straight line path between X-ray source and detector. When X-ray beam passing through one slab of tissue, you can see here the intensity of transmitted X-ray is related with the intensity of incident X-ray, and in this case we can find out the linear attenuation coefficient. So when one X-ray passing through a slice, it is attenuated as follows: mu is equal to 1 upon 1x log to the base e n0 upon ne. If the two slices in the path of the beam, then the same equation can be utilized, and therefore sum of mu1 plus mu2 is equal to log E n0 upon nx upon into 1 upon x, which is the thickness of voxel. Now let's see how the scanning and data acquisition phase takes place. I was telling about how this scanning phase takes place. The scanning phase involves the data taking by rotating the X-ray tube, and the X-ray transmitted through patient. The detectors on the other side of the patient acquires the data from one projection, and then when X-ray tube is rotated, it takes multiple projection across the patient body. About 1000 projections are taken when X-ray tube rotates about the patient body in one rotation. Now let's see the slice thickness, the relation between slice thickness and matrix size. Slice thickness is equal to field of view upon matrix size. That means the pixel size is equal to the image size upon the matrix size. The voxel is in three-dimensional, as you can see here, the voxel and the pixel. This is the voxel, this is the pixel. So particular slice is scanned by rotating X-ray tube with 360 degree around the patient body, taking multiple projections. 1 degree, for example, it takes about 3 projections, so 360 degree, about 1080 projections are taken. And in one projection there are 800 scanned data, or 800 rays are collected. So measurement of transmitted X-rays by an array of detectors is done by using the equation, as I told you, the logarithmic of the ratio of transmitted and the incident radiation gives me the value of total linear attenuation coefficient. So these data acquired once the X-ray tube together with the detector assembly moves around the patient body, as I showed you in my figure. The transmitted radiations are detected, and each projection takes thousands of data. That means the number of detectors, about 700 to 800 detectors are mounted in one row, and therefore 800 data are collected when the X-ray beam is fired from one projection. As I told you, thousands of projections are taken. Now when 256 slabs of tissues are there, in that case you can see the entire slab is as if cut into 256 slabs of tissues, and the value of the transmitted radiation passing through one ray gives the sum of the mu's, that means sum of the linear attenuation coefficient. Now this values are the raw data. So the second step is the pre-processing of raw data. How do we pre-process the raw data? This pre-processing of raw data involves the logarithmic of ratio of transmitted radiation, incident radiation and transmitted radiation, and then this pre-processed data is sent to the array processor to perform the data processing and then display the image. Now third step is image reconstruction. The image reconstruction involves sending pre-processed data into array processor, and the array processor process the data information and then it sent it back to the computer. So processed data are in the form of individual value of linear attenuation coefficient. So there are three methods of image reconstruction. One is iterative, simple back projection, analytic function methods are filtered back projection, and Fourier reconstruction. Usually filtered back projections are very important, very common in X-ray in CT reconstruction techniques. In iterative reconstruction technique, it uses a series of calculation that runs repeatedly. After each runs, the resulting image appears more and more like the actual image during the iterative process. The present interaction image is used to calculate each projections. Iterative reconstruction starts with the assumption that all the point in the matrix has the same value. This assumed value is compared with the unassumed values. The error between the measured and calculated CT projection are then used to update the image for the next iteration. In that case, you can see here the iterative methods have been used to define how the total value of linear attenuation coefficient can be utilized to find out individual value of linear attenuation coefficient of each slabs of tissue. We can call it as voxel, which is three-dimensional representation of two-dimensional pixel. So we can find out. So what we have done is that during reconstruction process we can find out the individual value of linear attenuation coefficient. Now second projection technique is simple back projection. Here each data point in a projection is a transmission measurement made through the object. Here the image matrix is initially set to 0. For each data point in a projection, the transmitted value is added to each pixel in the image that corresponds to a linear path through the object. For example, if the object is scanned from both the top and the left side of X-ray beam, and when the rays from two projections are superimposed or back projected, they produce a image of original object. So initially the total value is projected back equally in all the voxels, and then the data are summed up from different direction and it is utilized to reconstruct the image. However, in simple back projection, the image of the object is not projected. There are some degradation exactly initially near the periphery of the image. For example, if you want to see an image of a spherical object, this spherical object will be when image is formed using simple back projection, the image of a spherical object will look like exactly like a star-like pattern. So this is usually reduced by using another method called filtered back projection. As I told you, this is very common method. It is used in almost all scanner today. It is similar to back projection, except that image is filtered to counterbalance the effect of sudden density changes which causes blurring as in case of simple back projections. Projections are modified by introducing a negative functions so that when back projection is performed, the negative values cancel to the image except the appropriate location. Next analytical function is the Fourier analysis. Of course, it is not used in CT. The basic of Fourier analysis is that any function of the time or space can be represented by sum of various frequencies and amplitude of sine and cosine values. This Fourier transformation is very popular in MR imaging. Now next step is conversion of linear attenuation coefficient into the grayscale by using Hounsfield unit. After computer calculation, a value of linear attenuation coefficient of each pixel is known. This value of linear attenuation coefficient is converted into CT number or Hounsfield unit before assigning the grayscale. So you can see here the CT number is equal to mu of the pixel minus mu of water upon mu of water into 1000. Mu pixel is the pixel linear attenuation coefficient of that pixel. Mu water is the linear attenuation coefficient of water, and K is the magnification factor, which I told you it is 1000 here in this case. Then the CT number is called Hounsfield unit. This Hounsfield unit is actually in the order of thousands, minus thousands to plus somewhere around 3096. So if the mu of pixel is equal to the mu of water, then CT number is 0. This CT number varies from minus 1000 to plus 1000 for tissue. For water this is about 0. So this is the Hounsfield unit for different. For bone it is very high, it is about 1000. So depending upon the Hounsfield unit of each pixels, the grayscale is assigned. So the next step is display of image. In the display of image, the entire CT image of having 4096 shades of gray can be displayed are to be displayed on 256 shades of gray on the TV monitor, and therefore we need certain kind of post processing manipulation that is done by using windowing, window width and window level. Because the human eye cannot discriminate more than 32 shades of gray, because many soft tissues different only by a few Hounsfield unit. So we use this certain windowing. Window level is set according to the tissue in which we are interested in. For example, this window width is set according to the tissue we are going to see. For example, minus Hounsfield unit image is dark, plus Hounsfield unit image is white. Window level of, let us say, 50 for abdominal tissue, window level of 750 for lung tissue. Window width determines the grayscale representation of tissue. Wider the window width, longer the grayscale. Narrower the window width, narrow is the, so you can see the high contrast. Window level is the center of the window level, is the center of Hounsfield unit which we want to see. Window width is the range of CT number. Above and below CT number becomes saturated. For example, in this case the window level is set between 0 to 256. So less than 0, everything becomes black, and above 255 everything becomes. Similarly, limits can be set from minus 50 to plus 50, that is always below minus 50 is complete dark, image above plus 50 is completely bright. So in that case even the soft tissue and bone will be brighter. Image is displayed on different shades of grayscale between minus 50 to plus 50. So the window width is here is 100. The entire image in grayscale is being displayed between Hounsfield unit of 100. So this tells you about the contrast of the image. For example, a thoracic CT scan can be displayed with a lung window, a liver window and a bone window. Now coming to the next step is the CT generations. There are, first generation was a translate rotate type. In this case you can see a pencil beam is used. It was used for brain scan. Enclosing patient, his head scan was enclosed in a water bath, and detector below which synchronized. This uses only one detector, and X-ray tube as well as detectors, then only one detector is used and it translated. Detectors were sodium iodide activated coupled with photomultiplier tube. In this case you can see here the first generation CT scanner, a pencil beam is used, and first X-ray beam is translated from a particular angle. The X-ray beam is translated. It used to take 160 measurements, and then when it completed one translation movement, whole tube together with the detector assembly rotated, and again the transmitted translational measurement was repeated to acquire the next data. This was repeated until 180 degree projections were acquired at 1 degree interval. The advantage of first generation CT scanner was this was pencil beam, so scattered radiation is very less. But disadvantage is that very long scan time. It was about 5 minutes per slice. So you can see it used to take more than an hour to complete the entire slice. Complete complex mechanical translation, mechanical engineering point of view, this is very complicated. This was used to be very complicated. Second is the again translate rotate type. Again here X-ray tube and together with the detector assembly took the translational measurement and then rotational measurement. But here the number of detectors were increased from 1, as in case of first generation CT scanner, to 30 detectors. It used a small fan angle. There was an increase in the number of data per projection and number of projections. The movement of X-ray tube detectors array are both linear and rotate like in the first generation CT scanner, but rotative steps were much larger and therefore the scan time was reduced. So the advantage of second generation over first generation is that here the scan time was reduced from about 5 minutes to about 20 seconds per slice, and the speed increases because of the increased number of detectors assembly. The multiple detectors gathers more data per linear scan, so fewer linear measurements were needed and therefore the scan time was reduced. Instead of moving primary gantry rotate step to 30°, hence reduced scan time only up to 6 times. But again here there was a disadvantage of second generation CT scanner, was that increased scatter radiation as compared to first generation CT scanner, complicated mechanical motion of translate rotate. Again sodium iodide detectors were used, which were afterglow problem was there, complex mechanical rotation. Then third generation CT scanner was introduced into the market. This was rotate type. That means both X-ray tube and detectors rotate around the patient body in a concentric circle whose center approximately coincide with the center of the patient. It uses fan angle between about 42° to 49°, and detectors were perfectly aligned with the X-ray tube. Original scanners were uses 288 detectors. Newer version of third generation CT scanner used up to 700 X-ray detectors. You can see here the both X-ray tube and detector assembly moved around the patient body, and it is a rotate type because both X-ray tube and detector are moving, are rotating. Advantage of third generation is that here the excellent image resolution, image contrast with the short scan time. Xenon gas field detectors were also used, which is highly directional and efficient rejection, but disadvantage that cable wear and tear problem was there. Cone beam artifact was the problem. Then occupational appearance of ring artifact was there with the third generation CT scanner, and reduce these problems. Fourth generation CT scanners were introduced. This was rotate stationary type. That means detectors were stationary, however the X-ray tube only moved around the patient body, and detectors were in a ring shape around the patient body, and when X-ray beam was used to rotate, the X-ray tube rotated and the transmitted absorption measurements were made by using ring of detectors. This eliminates the ring artifact. Due to fixed detectors, tear and wear problem was completely eliminated, but disadvantage that this lead to high patient dose since the distance of patient from the tube is minimized. Secondly, more scatter radiation, and because of the more number of detectors were added up, the cost was the problem. It used to be high costly. Fifth generation was stationary type, so there was no X-ray tube. It was used for cardiac application. It is used to image the anatomy, but essentially helpful when fast imaging was used. You can see here in this figure there is a electron beam which is produced by electron gun, and this electron beam is rotated, steered on a fixed tungsten detectors. tungsten ring of target, and it produced X-rays. As electron gun with a spoke sink cuff, deflection coil, tungsten target, 180 centimeter in diameter, ring of detectors. Workings that waveguide was used to accelerate the electron beam onto a target through bending magnets to produce X-rays and collimate it into the fan beam. X-ray beam passing through the patient, the other side of the patient is enclosed by the detectors. This detector was in about 210 degree and rest is closed by tissue with same time that the target with 2 rings of detectors were used. The next scanner type is the spiral CT. Here the helical scanning uses 3rd generation or 4th generation slip ring design. Slip ring in circular contact with the sliding brushes that allow gantry to rotate continuously. That actually completely changed the scenario of helical CT scanner. Data can be transmitted to any desired plane, like coronal plane, sagittal plane, because the patient is moving around the patient gantry, and simultaneously gantry is also rotating. So the gantry is rotating in a circular fashion, tube is rotating in a translational fashion. You can see here in this figure. So this combined motion of translational and rotational motion traces a spiral path on the patient body, and this is what is called the slip ring technology, this is called spiral CT. Now let's see how it is the slip ring technology. It allows the gantry to rotate continuously without interruption. There are 2 slip ring design is used in the spiral CT scanner. One is the disc and other in the cylinder type. This design incorporates a ring parallel to the plane rotation, and cylinder design has a conducting ring lying parallel to the axis of rotation. Now pitch is equal to the translational measurements per gantry rotation divided by the slice thickness. Increased pitch increases the volume of tissue to be scanned. The brushes transmit power to the gantry component to guide in contact grooves on the stationary slip ring made of silver graphite alloy. There are usually 3 slip rings are on the gantry, you can see here. Now coming to the MultiSlice CT scanner, multiple rows of detectors are used instead of using only 1 rows of detectors. Multiple rows detector allows registration of more than 1 channels per gantry rotation. It started with the 4-slice CT scanner. It means that there were 4 channels and different rows of detectors were used. In fact, there were 2 type of technology used initially. One was used fixed array detector technology, and other one was used as a adaptive array technology. In fixed array technology, detector width used to be fixed. Let's say for a Wipro G scanners, they had 16 rows of detectors, and width of each rows of detectors were 1.25 millimeter each, and there were 4 channels, so it could acquire 4 slice per rotation, and number of rotations were increased from 1 rotation per second to about 2 rotation per second, and therefore now it is 3 rotation per second. So the number of speed of X-ray rotation was increased. Now last section is the dual energy CT. In fact, this dual energy CT is the current type of CT scanner. The dual energy CT has dual source dual energy, single source dual energy CT, single source dual energy with the dual detector layers. See, advantage of these detectors, these type of CT scanner are, you can see CT angiography you can do, high temporal resolution is possible for cardiac application, scanning without beta blockers, which means that the rate independent of temporal resolution, less dose for the patient, especially for the obese patient, faster cardiac acquisition with the shortest breath holder, ability to scan asthmatic patient, asthmatic patient, possible to differentiate body fluid. But the disadvantage is that temporal misregistration, since the scan not done simultaneously but a small gap. Limited dual energy like 33 centimeters, which makes it difficult to image patient with a larger body, and moreover doses are slightly more as compared to single slice CT scanner. The summary is that CT scanner yields a cross-sectional image in different plane. CT employ different reconstruction techniques to reconstruct the image from projection measurement made around the body, taking multiple directions. Usually filtered back projection techniques are used. Some of the CT scanners nowadays are using iterative methods. Nowadays multiple detector technology, multiple detector CTs are increasingly being used. We have 64, 128 slice, 256 slice, and 12 slice CT scanners are increasingly being used. We have the dual energy CT scanners. So all these CT scanners are utilized. They perform better Z-axis resolution, better image contrast, and image resolution is very much improved with a minimum scan time. So it provides different three-dimensional post-processing technique can be used to further add up in the diagnosis of soft tissue pathology. I thank you very much for your patience hearing.